So yeah, we heard a very good example of the acceleration and how data are being used on a test system and how you can accelerate your testing by bringing the field into the lab by Stefano from Streparava. So the motivation is, I mean, most of us are, yeah, we all need to ensure that our products are meeting specified requirements in the field. And why do we go into the laboratory? So there's different reasons. One, real-world conditions are very complex, and it's a lot of effort to test all these conditions. I mean, we can't take a vehicle out on all the different roads into all the different climatic regions, and we can't evaluate all the different drivers. We have to reduce the space of possibilities somehow. And have less complexity. We need to focus on a subworld of that reality. So sometimes we're only evaluating a component of a very complex specimen, so maybe only an axle instead of the full vehicle. And we also want to control the conditions, so ambient temperature, the way how the test is being performed. That's another advantage why we want to go into the laboratory. And another reason is the acceleration of the test itself. So when we're on the road in real conditions, we don't have that pothole once after the other. We always have to kind of go back and make turns and go back into the pothole. So on a test rig, you can cut out that one event and you can repeat it as often as you want. So this presentation is talking about what needs to be done when you bring the field into the lab. So these pictures are showing some examples of the complexity of these real world conditions. There's different road surfaces. In your world it's maybe not roads so much, but it's the ground, the surface of the soil you're working on. It's the weather conditions. Sometimes it's very wet and slippery, very heavy soil. Sometimes there's a lot of dust which might cause problems to electronic components or bearings or whatever. You're using your equipment in many different ways, by pulling stuff, by carrying stuff, by maybe using it to lift things and move them around. So there's a lot of different applications. When you build a tractor, you might not know what all these applications are. Same as for trucks, there's special applications for trucks with wood choppers where they cut trees to chop woods for heatings. So there's many different applications that you might not be aware of when you're designing your product. The first step you're doing probably is analyzing the mechanics of the system. So when we take this this excavator here as an example, and you're focusing on the level arm of this excavator, so what are the critical conditions? You can cut free mechanics. You have a bearing here, you have a level arm, you're moving a mass around, you're lifting it, you're kind of turning the arm. So what is the load path in your structure? You have a finite element model that describes these typical loads. And when you're doing a measurement, you might want to find the spots where you would gain relevant information. So when you apply strain gauges, where are the weak spots? Where do you have stress concentration? Where can you learn from your structure while you're doing a measurement? And then maybe when you see this two-dimensional problem, you're looking at the loads, but what happens when the whole excavator is making turns and stopping? There's a side load on the whole structure, which might also cause or will cause damages. Also the ambient conditions, so when the thing is moving in the ground, there's a difference whether it's dry sand or whether it's wet soil, or maybe it's even winter time and the soil might be frozen in some areas. In this case, maybe where you have a very simple load history, the signal of the loads that you're acquiring on this component or on this system might be rather cyclic loads, loads that you can count in events. You can say, I'm lifting dirt every minute, and I'm dropping it into the back of a truck, something like this. So you can count these cycles, and you have a more or less repeatable signal in this application. Other applications where you might acquire data on a vehicle that's driving along on a rough road, or components that are mounted on the engine. You might find data that are not so periodic in the sense that you have something like a sinusoidal load input. So in some cases you might have very wild signals. These raw data that you might find are they have different frequencies involved, higher frequencies coming from the engine or from cobblestone on the roads. Then there might be lower frequency events from braking or turning, things like that. So when you want to gain this information, you need to find the spots where you would acquire these loads. You can take a wave force transducer, as Stefano just has shown, to acquire forces and moments directly on the wheel hubs. In some areas it's very helpful to add strain gauges, so you can go to your structure, you can see what the response of your structure is, not only what the input signals into the wheel hubs are. You can use accelerometers to evaluate the behavior of your structure, or like in this example down here, you might use an array of force transducers to derive you a 6 degree of freedom load history on a shovel of an excavator or lift truck or something like this. So the target of this here is to gain information from the field, data that you can use as an input for your test. So then you will do some little bit of data processing. You can do this in RPC Pro. RPC Pro offers a range of methods and tools that can be applied to process the data. So there's a filtering of the data. You want to remove artifacts. You want to focus on the frequency range that's really relevant for this test and application. You maybe want to cut out areas that are not relevant for the specific test. And then you will do something like a damage-based analysis of these measured data, so some fatigue analysis. Loads will be put into relation with lifetime or the mileage, and you will apply counting methods like range pair or rain flow counting methods that quantify damage per time or mile. So then it's about the input signals for a test, the loads that are derived from these measured data are forces or moments, it's accelerations or displacements, it's strain signals. Most of these signals can be used to control your test system. And then the question is, what is the shape of these input signals? So is it a very simple sinusoidal test, something I can generate signals in an artificial way? Do I have some block cycles? Do I mix certain amplitudes? Or do I have time histories? So if the setup is very simple, the complexity of the load pattern is rather simple, a sinusoidal test input is reasonable. If you have a dynamic structure, some very complex structure, and a mix of different damaging events that all maybe have certain time history that is required to replicate these loads. So there's a phase relationship to the of the loads and the behavior of your specimen. Then you will need to go to time histories and the replication of time histories. So the complexity of the load history in the specimen is very important. And from that we can derive the type of the signals that we will use for the test. So this is an example of a rather simple test. It's an anti-roll bar. In this case, it's mounted in a vehicle subframe, and there's not a lot of dynamic involved in this test. We have a mix of some quasi-static loading conditions and then sinusoidal load inputs. You can see this test setup is a very simple component test with an actuator pulling on one side of this anti-roll bar assembly. We have different application software that you can use to run tests like these. Let's say the older version is the MPT software that we talked about, the multi-purpose testware. This software is using a test line, a timeline and test procedure, so it's a sequence of things that you do after each other. It's very configurable, and it's based on the 793 on the Flex test software. The new application software that's eventually replacing MPT in the future, once all the features are implemented in the software, is the multi-purpose software test suite. This is built to cover more complex test procedures, and the logic that we're using in the test suite software is more like a flow control design. So you have different modules, and you can click these modules together, and you can, for example, have a sequence where you load data, you filter data, you have a module where you define the filter, then you send the filter data into the next step, and step by step you're processing the data and you're running them through the test sequence. So test suite allows the full control of your test. There's the test definition. It contains many components, procedures, variables, test run displays, resources, functions, and also report templates. So you can configure the whole test from the input signals up to the way how the report should look like. Then there's a control panel that allows you to reset interlocks, to manage the station pressure, and to start the test. And then there's also the run test application, where you have information about the numbers of cycles you're in, or the time you're in, what the signals look like, a comparison of the target signals and the real data, and also maybe damage-related information about your specimen. You need to ensure an accurate control of your test. Flex test controllers are very robust. We offer a modular architecture, so it's adaptable to changing needs in your laboratory. In the software you can reconfigure your component test area. You don't need to rewire the different stations when you pull in more actuators into your test. It's all configured within the station manager and station builder in the Flex test software, and we have many compensation techniques. So amplitude and phase control, peak valley control, adaptive inverse control, and many more compensation techniques that will help you get an accurate control when your specimen behavior is not as linear as you expect, or when you have a damper that goes into the Jones bumpers, things like that. There's a way that we can handle these events. We have calculated channels, so you can make use of different informations from sensors and calculate channels that you use for the evaluation of your test. And then we are featuring EtherCAT, a digital interface to help you to talk to the vehicle bus. There's gateways to talk to FlexRay. We can very easily integrate a different number of data acquisition systems. There's an interface to talk to CAN, to your vehicle networks, and there's more interfaces and protocols that are supported through EtherCAT and Modbus, for example. The future focus on the development of flex test controls, we're working on the performance of the flex test controller, and also we're continuing to work on the connectivity, so we see that the mechanical hardware in the loop, so very often a super simple component test with an anti-roll bar becomes not so trivial anymore if there's an active control element in that anti-roll bar. So you have to have some signals that help the ECU or the control unit of that anti-roll bar to believe it's somewhere in the field. You have to feed it with the velocity, for example, and with a steering wheel angle or something like this. So you have to add information to the physical test, and this connectivity is very important for future applications. Then when we have a more complex test, I hope the video plays. Yes, it does. So this is a full vehicle test on a small four-wheel ATV. It's a full vehicle test. It's testing the suspension system, and you can see there's additional load input that simulate a little bit the behavior of the driver, and the loads are being applied into the handlebar, for example. And so you can also see that there's a clear relationship of the phase of the signals in the specimen. So this is nothing you can just do with sinusoidal load inputs. So for a time like this, we want to replicate the time histories that we measure in the field. For this, we use the RPC Pro software. RPC stands for Remote Parameter Control. And RPC originally is a control technique. So when you have the actuator is controlled by a displacement or a force, but the signal you are trying to replicate is the acceleration on the vehicle or the force on a V-force transducer. So remote refers to not controlling the system to the sensor that's built into the actuator, but it's remote on your vehicle. This example on the right shows a little bit also the acceleration on the timeline here. So the customer is using the vehicle on a road many thousand kilometers. So most of our customers, the OEMs, have some reference test tracks where they say, if I ride my vehicle on this test track for 1,000 miles, this equals 100,000 miles in the field. And there's a lot of historic knowledge, tribal knowledge in there. There's mostly some events that happened in the 70s and 80s, and then they built their test tracks. And if you go to these test engineers and ask them why the test track looks like it looks, it's just history and it just looks like that. And it's very interesting when you see a couple of years ago there was something like a round-robin test in Germany where some customers shared vehicles in the labs of other OEMs, and they were running the test. They were not exchanging any information about the design of the vehicle or the data itself. They were not telling what kind of data they used. They were just running an endurance test over these test tracks. And then they were bringing back the car, and they saw that most of the vehicles are kind of over-engineered in specific areas, because in some many years back there were failures, and then they focused on this thing. They built their test track to focus on these things. And most of the OEMs have different areas where they are focusing on and over-designing. So that was kind of interesting. But when you go on the test track, you have a number of events. And when you go in the test lab, you can even cut out some of the parts of the signal that are not relevant for the damage, and then you simulate the remaining parts of this test lab. So that's some acceleration in both time and damage. The RPC software can be used for the data validation and for the editing of the data. So there's an analysis part where you can look at the data and analyze how the data look like. Then there's a model and simulate section where it is about to characterize the system, which contains the specimen and the test system. So the 329, for example, and the test system, the specimen, they are the system, and we generate a model from the frequency response of this model. And then we start to iterate the drive files. We teach the test system how to shake the vehicle in order to replicate the data. And then we can run the test and monitor how the test specimen behaves while we're conducting the test. The drive file generation with RPC, we are generating and analyzing frequency response functions. We can evaluate the cross-coupling between different channels. We can determine the correlation of the output to the input, the magnitude and the gain, and the phase and linearity. Then we derive and calculate the first and initial drive file. We're playing out the drive file with a relatively low gain. And then we see how the response plays out compared to the target data. And then we're making corrections on the model in an iterative process. And while the deviations between the target signal and the response goes down, we can increase the gain until we say the data converge, that we are good enough to use this set of data as a set of drive files, and then use these data for our test. We also have adaptive inverse modeling techniques, turbo RPC, that can adapt the system model according to changed specimen characteristics. So while we are increasing the gain, we might run into nonlinearities of our specimen, and that can also be adapted in the model. So again, the complexity of these daily challenges make our jobs interesting and diversified, and we offer a great variety of products and tools that will help you to solve these needs. And we have a service team that offers consulting through all the steps in the process, from acquiring data, from the question of where we should measure information on your specimen, which data are useful to conduct a test, how should the data be prepared for a test, and we can also help you in the process of generating drive files, for example, when you have a very non-linear, very challenging specimen on your test system and you're running into trouble while you're trying to iterate these tests. Also, when you're facing issues with the test system, the system is not behaving the way you are expecting it. These system integration engineers and STECs are very helpful to identify the problems and find a solution. Also, there's a number of different training classes. So there's training classes on the 793 software, on the Flex Test software, on the different modules that we're using. There's a fatigue training, classes about the fatigue. We can offer training on the digital interfaces, or on the RPC software on different levels. And then also, everybody who's using RPC is invited to our RPC users group meetings. So we have users group meetings worldwide. In Europe, we have users group meetings in the US and in Asia in different countries. So these RPC users group meetings are a forum similar to this one, but it's about RPC mostly. We're sharing experience about RPC with amongst our customers, so it's a very open forum where you can discuss issues and challenges you were solving with RPC. And we also have a number of our RPC experts, the STECs, on these meetings that can give some training and some introduction of new tools, and it's a very valuable community. Thank you very much.